Hello, students. Do you remember in the chapter on alkynes, I discussed a reaction involving the catalyzed addition of water to a carbon-carbon triple bond? The initial product has a hydroxy group bonded to a CC double bond. The product is called an enol. Remember that the enol is not stable and spontaneously rearranges to a compound with a carbonyl group. This will be either a ketone or aldehyde. This compound is referred to as the keto form or keto isomer. Note that the enol and keto forms are constitutional isomers. In this video, I want to show you more about the conversion of an enol to a keto isomer. It turns out there is more to the enol to keto isomerization than you might realize. Let me explain. What we find is that every compound with a carbonyl group, when it exists in pure form or in solution, is naturally in equilibrium with its enol isomer. For example, the common chemical acetone, in its vapor form at room temperature, naturally coexists with its enol form. The two forms are in equilibrium. How much of the acetone is in the enol form? The amount is extremely low, namely 0.00000024%. The very low concentration of the enol form reflects the fact that the enol form is much less stable than the keto form. The fact that the keto and enol form coexist in equilibrium implies that there is a chemical conversion from the keto to enol form, as well as the reverse, the conversion of the enol to the keto form. What I want to describe now is the actual chemical mechanism for the conversion of the enol to the keto form, especially in the context of the addition of water to alkyne reaction that was discussed in a previous chapter. An important point about that reaction is that it's acid catalyzed, so the conditions of the reaction are acidic. In this context, the conversion of the enol form to the keto form is in fact catalyzed by acid, that is, hydrogen ion. Let's start with a simple enol form in an acidic environment and follow its conversion to the keto isomer. Now, the goal is as follows. In the enol, transfer a hydrogen atom from the hydroxyl oxygen to the alkene carbon not bonded to oxygen. Mechanistically, this does not happen in a single step. Let's see how it actually happens. A hydrogen ion first attaches to the alkene carbon not bonded to oxygen to form a cation. Notice that the cation that results has resonance stabilization. Thus, this is a favorable process. Now, a neutral molecule is almost always more stable than an ion. So there's a natural driving force here where the cation converts to a neutral molecule. This happens simply by a loss of a hydrogen ion from the oxygen. So mechanistically, The enol is converted to the keto form under acid conditions in 2 steps. Step 1, a hydrogen ion attaches to the alkene carbon not bonded to the oxygen. In step 2, a hydrogen ion is lost from the oxygen. In conclusion, I just want to stress that the keto-enol isomerization is a very important process. We will encounter it again a number of times in different chemical situations. Today, we learned that the process is acid catalyzed. Later, you'll see a situation in which that process is also base catalyzed. So stay tuned.